Welcome to exam 3, problem 3. In this one we have a ring with a radius of 0.05 meters sitting in a 10 Tesla magnetic field, and then the field quenches. The magnet quenches, which is to say it abruptly turns off, and the field strength drops to 0 Tesla in just 20 nanoseconds. So the angle between the surface vector for the ring and the magnetic field is 0. Question is, what is the induced EMF in the ring when the magnet quenches? Well, if we pop over to our equation sheet, we will find that the induced EMF is minus delta phi b over delta t, and that phi b is the B field times the area times the cosine theta. So let's put it all together. Induced EMF, right, is minus the change in the magnetic flux divided by change in the time over which it changes. The magnetic flux is B field times the area times the cosine of the angle between the surface vector and the magnetic field. In this case, that angle is 0, so this is just going to give me BA, right? And A is pi r squared for the ring, so this is pi times 0.05 meters squared. Let's find A real quick. Pi times 0.05 meters squared is 7.854 times 10 to the minus third square meters. Alright, that's the area. Magnetic field is 10. That means the magnetic flux when we start is 7.854 times 10 to the minus 2, right? Tesla meter squared. That's where the magnetic flux starts. Where it ends is 0. Amount of time it does it in is 20 nanoseconds, right? So the induced EMF in minus, okay, so here we have our ending flux, right, our final flux minus our initial flux. Put the right units on the first one. Right? So that's the change in flux. And remember, it's always final minus initial, and this happened in 20 nanoseconds, or 20 times 20 times 10 to the minus 9 seconds, right? That's nanoseconds. So what does this equal? Right? Okay, so that minus goes through to cancel out that minus. So 7.854 times 10 to the second over 20 times 10 to the ninth. Right? Okay, just need to multiply that by the 10 to get us to our actual flux, change in flux. And we want that change in flux divided by 20 e minus 9, and so we get 3.9. So I'm going to go with 3.9. I'm not going to worry about the rest. It's 3.9 times 10 to the 6th it was volts. It's 3.9 megavolts. 3.9 megavolts induced in the ring. And that's the end of problem 3.